Hi everyone. Today we're going to be looking at 4.2, which is solving systems of linear equations using the substitution method. Let's begin by reviewing what we've learned so far. We've learned that a system of linear equations consists of two or more equations with an x and a y. The solution to a system of equations is an ordered pair, x comma y, and it's where the lines intersect. One method to solve a system is to graph both equations. And that's the first method that we learned in 4.1, solving systems by graphing. So suppose we have the example below. We've graphed these two lines on the same plane, and we're looking to find the solution. We know that the solution is where the lines intersect. So I'm looking at these two lines here, and I can see that they don't quite intersect exactly on the grid lines. As you can see, graphing might not be the best method for this problem since the intersection point does not fall on integer values or on those grid lines. If you are not accurate when graphing, or if the coordinates on the intersection points are not integers, solving a system by graphing may not be the best approach. Fortunately, we have other ways to solve systems. One of them we'll explore today, and that's solving using the substitution method. So in example 1, let's go ahead and try this example, x plus 2y equals 9 and negative 3x plus y equals 1. Our steps to solve is to solve for either of the variables. So if we have any variables in either of the equations that have a coefficient of 1 or negative 1, generally that's what we're looking for. That's going to be pretty easy to solve, usually 1 or 2 steps. So I noticed that in the very first equation, let me just rewrite both of these equations, x plus 2y equals 9 and negative 3x plus y equals 1. I noticed that in both of these equations, we have a coefficient of 1. In the first equation, we have a coefficient of 1 in front of the x, and in the second equation, we have it in front of y. So for either of these equations, I can just do one step, and that's going to get me x equals or y equals, which is what we're looking for. We're looking for x equals something or y equals something. We want to get x or y by itself. Step 2, or before we get to step 2, we have to solve for x or y. So I'm just going to choose the first equation, x plus 2y equals 9. In order to get x by itself, I'm going to subtract 2y from both sides. So if I have x plus 2y equals 9, subtracting 2y from both sides gives me the equation x equals negative 2y plus 9. Or you might have 9 minus 2y. So step 2 is to substitute this into the other equation. So in for x, I can plug in, so let me use a different color. I'm going to plug in negative 2y plus 9 into the other equation for x. So writing out this equation, I have negative 3 times x, but instead of x, I'm going to substitute in negative 2y plus 9, and then I'll finish off that equation. So that is the plus y equals 1. Okay. From here, we can solve for y. We've got a single equation with a single variable. So distributing the 3, we get a positive 6y. And negative 3 times positive 9 is negative 27. And then plus y equals 1. Combining like terms, 6y and 1y gives us 7y. Minus 27 equals 1. And then adding 27 to both sides. Oops. Adding 27 to both sides gives us 7y is equal to 28. And last step, dividing both sides by 7, we get y is equal to 4. Now what we can do is take that solution, y equals 4, and we can plug it back into either of the original equations. And I want to underline original. If we made any errors moving this over and solving for x, then if we were to plug it into this equation, we would be finding our other solution from an error, which would cause our x to contain an error. So I always like to go back to the original equations because we know that that's what's been given. We know that there's not an error in there. So I'm going to plug in y equals 4 into either one of these equations. It does not matter which equation you plug it into. I'm going to plug it into the second equation. So we have negative 3x plus y, but we know that y is equal to 4, equals 1. So we have negative 3x plus 4 equals 1. Subtracting 4 from both sides, we get negative 3x is equal to negative 3. And dividing both sides by negative 3, we get x is equal to 1. Now we're not done yet. We have to express the solution as an ordered pair, x comma y. So our solution, x, y, is 1, 4. And that's our solution. Last but not least, we got to check both of the original equations. And again, I'm going to underline original. And we're going to plug in our xy coordinates into the xy of each of the equations. So in the first equation, x plus 2y equals 9. I'll just copy that down here. And then our other equation was negative 3x plus y is equal to 1. So now we're going to plug in 1 for x and 4 for y and see if that causes the equation to be true. Evaluating the left-hand side, we get 1 plus 8 equals 9. 1 plus 8 equals 9, and 9 does equal 9, so that equation checks out. For the other equation, we're going to plug in, again, 1 for x and 4 for y. And evaluating, negative 3 times 1 is negative 3 plus 4. And negative 3 plus 4 does indeed equal 1, so that checks out as well. So we know that we've done this correctly. Let's move on. So example 2a says find the solution from the graph. So this is a review of 4.1. Remember, the solution on the graph is where the lines intersect. So I see that they intersect right here, which has coordinates negative 2, 0. But now I want to verify this solution by solving the system using the substitution method. So here are the equations of the lines, x plus 3y equals negative 2, and negative 4x minus 5y equals 8. Let's go ahead and solve using substitution. So rewriting these equations, x plus 3y equals negative 2, and negative 4x minus 5y is equal to 8. I'm looking for an x equals equation or a y equals equation, or at least a variable that has a coefficient of 1. And I see that we have that right here. So we have that x has a coefficient of 1. So in that equation, all I have to do is subtract 3y from both sides, and that's going to get x equals negative 3y, not plus 2, minus 2. There we go. And now what we can do is plug in negative 3y minus 2 into x in the other equation. So I'm going to plug it into the original here. So we have negative 4 times x. Well, x is negative 3y minus 2. And then we're going to finish off that equation. Minus 5y equals 8. Solving for y, we distribute negative 4. So negative 4 times negative 3 is positive 12y. And negative 4 times negative 2 is positive 8. And then minus 5y equals positive 8. And we combine like terms. So 12y minus 5y is 7y. Plus 8 equals 8. And then subtracting 8 from both sides, we get 7y is equal to 0. And then dividing both sides by 7, y is equal to, well, 0 divided by 7 is 0. Now I can plug this into one of the original equations. So we have x plus 3y is equal to negative 2. But instead of y, I'm going to plug in 0. So we have x plus, well, 3 times 0 is 0, equals negative 2. X plus 0 is just x. Adding 0 doesn't change anything. So we get the solution for x, negative 2. So as an ordered pair, we have negative 2, 0, which if we look at our solution from graphing, does verify that solution. So we did this correctly. All right, let's try a few more. So example 3, negative x plus y equals 4, and x minus 2y equals negative 6. So here, again, I'm looking for an x equals equation or a y equals equation. I see that both equations are one step away. Let's do the first equation. Um, let's now solve for y first. So here we have negative x plus y equals 4. I'll go ahead and rewrite that. In order to get y by itself, we have to add x to both sides of the equation, and we get y is equal to x plus 4. Now we can take that x plus 4 and plug it for anywhere we see y in the other equation. So we have x minus 2 times y, but here we're going to plug in x plus 4. And that's all equal to negative 6 from the second equation. Now solving for x, we're going to distribute this negative 2. So x minus 2x minus 8 equals negative 6. Combining like terms, x minus 2x is negative x, minus 8 equals negative 6. Adding 8 to both sides, we get negative x is equal to positive 2. And then finally, dividing both sides by negative 1, we get x is equal to negative 2. So now we can plug in that solution into either of the original equations. Let's choose the second one. Doesn't matter. You could try the first one on your own and see if we get the same answer. I'm going to go ahead and show the second one. So we have x, or negative 2, minus 2y is equal to negative 6. Well, negative 2 minus 2y, we can add 2 to both sides. And we get negative 2y is equal to negative 4. And finally, dividing both sides by negative 2, we get y is equal to positive 2. So our solution as an ordered pair is negative 2, 2. Now, actually, I want to check this one real quick. So let's plug it into both of the original equations. So here in the first equation, we're going to plug in negative 2 in for x and positive 2 in for y. So we have negative 2 plus y, which is 2, equals 4. And as a reminder, we're going to plug in anytime we substitute anything in, whether it's checking your work or substituting in an expression into one of the other equations, always use parentheses. You've seen now that when we use parentheses, that causes us to distribute that number in front. So if we're multiplying this, we want to distribute to every term that we've substituted in. So it's good practice to use parentheses as you're substituting in. So here we've got negative 2, that double negative gives us a positive 2 plus 2 equals 4, and indeed 4 equals 4. For the other equation, we have negative 2 minus 2 times 2 is equal to negative 6. Well, negative 2 and then a minus 2, or a negative 2 times 2, is negative 4. And then negative 2 minus 4 is negative 6, which does equal negative 6. So that checks out too. So we've done this one correctly. Let's move on. Example 4, let's try another. Well, now we have a y equals equation. So I can just take this and plug it right in for y in the other equation. So here we have x plus 2 times y. Well, we know that y is equal to 3x. And we know all of that is equal to negative 14. Multiplying, we have x plus 6x equals negative 14. Combining like terms, 7x is equal to negative 14. And dividing both sides by 7, we get x is equal to negative 2. Plugging it back into one of the original equations, y is equal to 3 times negative 2. This is the first equation. So then y must be equal to negative 6. This causes our solution to be the ordered pair negative 2, negative 6. Let's go ahead and check our work just to make sure we did everything correctly. So plugging in to each of these equations, so negative 6 is equal to 3 times negative 2. 3 times negative 2 is negative 6, and that does equal negative 6. In the other equation, we have negative 2 plus 2 times negative 6 is equal to negative 14. Well, negative 2 plus, and then we have 2 times negative 6 is negative 12, equals negative 14. And 2 plus negative 12 is negative 14, which does equal negative 14. So this checks out as well. All right. Example 5. So this is from our textbook on page 157. Sadie and Micah use different methods to solve the system of equations. Sadie substituted in the expression 2x plus 3 in for y in the second equation, and then solved for x. Got the solution x equals 4. Then plugged in the solution for x into the other equation and solved for y and got 11. So Sadie got the solution for 11. Micah solved for y in the second equation and then set both equations equal to one another. And then solved for x and got x equals 4. Micah then substituted in 4 into the original equation and solved for y and got y equals 11 and got the solution for 11. So example 5a is asking in what ways are Sadie and Micah's approaches similar and in what ways are they different? Take a moment and think. What do you think? How are they similar and how are they different? One way that I noticed that they're similar is that both used a form of substitution. Sadie substituted in the expression 2x plus 3 in for y in the other equation. Micah just manipulated the second equation to solve for y, but then substituted in that equivalent expression in for y, essentially setting y equal to y, or those expressions equal to one another. And so, in a way, that is a form of substitution. So Sadie substituted for y, while Micah, there we go, solved both equations for y, and then set them equal to one another. And this is a perfectly acceptable method or approach to solving systems of equations by substitution. So, depending on which method you prefer, you are absolutely welcome to use either of these methods. And that's the answer to 5b. Are they valid solution methods? Yes, they are. Yes. Both used a form of substitution. Okay. Moving right on, example 6. Together, Karina and Nolan have a total of $36 to spend at the HP food trucks. Nolan has $8 more dollars than Karina. Let X represent the amount of money that Karina has and Y represent the amount of money that Nolan has. Follow the steps below to determine how much money each person has. Write a system of linear equations to represent this situation. Equation 1. So equation 1, we'll say that X is the amount of money Karina has. We know that Nolan has $8 more than Karina. So we know that if X is the number of dollars or the amount of money that Karina has, Y is the number that Nolan has. We know that Nolan has 8 more than Karina. So we can set up the equation Y equals X plus 8. We also know that together, Karina and Nolan have a total of $36. So if we add up the money that they both have, so X plus Y, then it should be totaling to $36. So now we have these two equations. Let's go ahead and solve using the substitution method. So I noticed that we already have a y equals equation, so I can just plug that in for y in the other equation. So we have x plus y, well, we know y is x plus 8, and that's equal to 36. So here we have, combining like terms, 2x plus 8 is equal to 36. Subtracting 8 from both sides, we get 2x is equal to 28. And dividing both sides by 2, we get x is equal to 14. We can then find the amount of money that Nolan has. By plugging in 14 in for x in one of the original equations. So y equals 14 plus 8. So adding 14 to 8, we get y is equal to 22. And so we have the ordered pair solution, 14, 22. So what does this mean in the context of this application? Well, we know that X is the amount of money that Karina has, and we know that Y is the amount of money that Nolan has. So that tells us that Karina has $14 and Nolan has $22. All right. Let's go ahead and graph both of these equations and find the solution graphically. So our two equations, again, are y is equal to x plus 8, and x plus y is equal to 36. So graphing these two lines, well, the first one is in slope-intercept form. We have a y-intercept of 8, and notice that each of these increments are by 2. And then our slope is 1, so that tells us that we have a slope of up 1 to the right 1. And I'm going to just draw a lot of points. So I'm freehanding this on the screen, so it's a little tricky. So the more points you draw, the straighter your line will be, or at least the easier it is to be an accurate line. If you're following along at home, go ahead and use a straight edge, use a student ID, use a calculator case, a folder, a ruler works best, but any straight edge that you have. And next we have x plus y equals 36. So this is in standard form. I can solve for the x and y intercepts by plugging in 0 in for y and for x respectively. So to find the x-intercept, I plug in 0 for y. That gives me an x-intercept of 36. I get a y-intercept by plugging in 0 for x, and that gives me a y-intercept of 36 as well. So connecting those dots, and we have this line here. And again, if you've got a straight edge at home, please use that. All right. So now we can see the point where they intersect is right here, which has the coordinates 14, 22. And so we've just verified this solution graphically. Oh, and we want to label the axes. Almost forgot. We want to label the axes. So the y-axis is the amount of money that Karina has. So and then the x-axis is the amount that Nolan has. Or I think I got those mixed up. Let me double check. Yeah, X is Karina, Y is Nolan. Okay, so I got those mixed up. All right, so y-axis is the amount that Nolan has, and the x-axis is the amount that Karina has. All right. Now let's take a look at some special cases. In 4.1, we learned that the system of linear equations can have no solution if the lines are parallel, one solution if the lines intersect at exactly one point, or infinitely many solutions if the lines are completely overlapping. Remember, we learned how to recognize this by looking at the equations and looking at the graph. We can tell by the equations whether they have the same or different slope and the same or different y-intercept. We can look at the graph. If they're crossing, they have exactly one solution. If they're overlapping, they have infinitely many solutions. And if they are parallel, they have no solution. Let's see what this looks like using the substitution method. So case 1 over here, we have parallel lines. Let's see what happens when we solve this system using substitution. Right now, they're both solved for y, so we can just simply set the equations equal to one another. So we get 4x plus 3 is equal to 4x minus 1. To solve this, I'll subtract 4x from both sides, and we get 3 is equal to negative 1. Now we have to ask ourselves, anytime we get to something like this, is this a true equation or is this false? Does 3 equal negative 1? No, this is false. 3 equals 3, and negative 1 equals negative 1, but 3 does not equal negative 1. So because this is false, this tells us that we have no solution. Or in other words, There is no xy coordinates or ordered pair that would satisfy both of these equations. There are, of course, infinitely many that satisfy each of the equations, but not both. Now let's consider case 2, where it's the same lines. Or remember, graphically, these are two lines that are stacked right on top of one another. So to solve this system, well, I see that we have not quite a y by itself, but it's one step away. So 2x plus y equals 3. If I subtract 2x from both sides, then I get y is equal to negative 2x plus 3. And that we can plug into the equation 6x plus 3y equals 9. So I'm going to plug in negative 2x plus 3 in for y in the other equation. Now we can solve for x, and we get 6x. And then 3 times negative 2x is negative 6x. 3 times 3 is 9, and then equals 9. Well, combining like terms, those 6x and negative 6x cancel, and we get 9 equals 9. Again, whenever you have a number equals a number, you have to ask yourself, is this a true or false equation? In this example, 9 does equal 9. That is true. So, because this is true, this system of linear equations has infinitely many solutions. All right. Last page, just some extra practice. Number 1, let's solve each of these systems using the substitution method. And we also have to determine if there's one solution, no solutions, or infinitely many solutions. If you'd like, you can go ahead and pause the video and try these on your own, or you can follow along with me now. Number 1, let's go ahead and solve that first equation. Let's solve for x. So subtracting y from both sides, and we get x is equal to 3 minus y. I'm going to plug that into the other equation. So we have 2 times 3 minus y plus 2y is equal to 4. 2 times 3 is 6. 2 times negative y is negative 2y. And then plus 2y is equal to 4. Combining like terms, negative 2y and positive 2y cancel out, and we're just left with 6 equals 4. This is a false equation, and so that tells us that there are no solutions. Number 2. Here we have a y equals equation, so we can just plug that expression right in for y in the other equation. So we'll plug this in for y. So we have 9x minus the quantity 9x minus 1 is equal to 5. Well, this here, this negative out in front, is just like saying negative 1 times that quantity. So what we can do is distribute that negative 1. So negative 1 times 9x is negative 9x, and negative 1 times negative 1 is positive 1. That's all equal to 5. And then we have 9x minus 9x is 0x, so that cancels out. We get 1 equals 5. Again, this is a false equation, so there is no solution. Number 3. Here we have x plus 3y equals 4. I notice that the coefficient for this x is 1, so that one should be pretty easy to solve for. I'm going to subtract 3y from both sides. And we get x is equal to negative 3y plus 4. Plugging in negative 3y plus 4 and for x in the other equation, we get 2 times the quantity, negative 3y plus 4, plus 6y is equal to 8. Distributing the 2, we get negative 6y plus 8 plus 6y is equal to 8. Combining like terms, those cancel out, and we get 8 equals 8. This is true. 8 does equal 8. So this tells us that we have infinitely many solutions. Okay, last one. 5x minus y equals 8 and x plus 5y equals negative 8. So this one has a coefficient of negative 1, so we could do that, but I think this one looks a little bit easier. So let's go ahead and solve for the x in the second equation. Subtracting 5y from both sides, we get x is equal to negative 5y minus 8. Substituting in that expression, negative 5y minus 8, into the first equation for x, we have 5 times the quantity, negative 5y minus 8, minus y is equal to 8. And distributing the 5 into both of those terms, we have negative 25y and minus 40 minus y is equal to 8. Let's see, combining like terms, so negative 25 and negative y gives us negative 26y minus 40 equals 8. And then adding 40 to both sides, we get negative 26y is equal to 48. And finally, dividing both sides, by negative 26, we get y is equal to negative 48 over 26, which can be reduced to negative 24/13. All right, so we got a fraction as an answer. Let's go ahead and plug that into y in either of the equations. Let's do the first equation. So we have 5x minus a negative 24/13 is equal to 8. So now we have 5x, and this double negative cancels out. So we have plus 24/13 is equal to 8. Subtracting 24/13 from both sides. And we get 5x is equal to 8 minus 24/13 is 80/13. And finally, dividing both sides by 5, we get x is equal to 16/13. And that cannot be reduced, so that's our final answer for x. So our solution as an ordered pair is 16/13 and negative 24/13. All right, so that one had one solution. All right, so that's it for our notes today. This is solving systems of linear equations using the substitution method. Just as a summary, we're looking for an x equals or y equals equation. If we don't have that, we're looking for any x or y terms that have a coefficient of 1, so that we can solve for that. Once we have that, we can plug in the equivalent expression into that variable in the other equation and solve. Once we have a solution there, we can plug that back into either of the original equations to solve for the other variable. Our solution is an ordered pair. All right, we're going to get plenty of practice on this in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.